Okay, so today we are going to first start off by reviewing the two different types of functions that we've talked about so far. First type of function is the linear function, which we all know graphs a line. And the rate of change for a linear function, we describe it as being constant. And as we all know, that with a line, what's constant is the slope. Okay, so for example, here's our equation y equals 2x plus 1. So if we make a table for the graph, again picking our x values, plugging them in for x, solving for y. These are our y values, our outputs for the function. Right, what you're going to notice, again, is in this table, right, that as we go from one output value to the next, right, we have to add 2 to get to the next output value. Right? And that 2 value is our rate of change. And it's constant. And again, with our function, that rate of change is the slope. Okay? So it's that constant rate of change which allows our graph, when we plot the points, to form the line. Right? So the next function that you learned was about the quadratic function. And we talked about the quadratic function. We know a quadratic function exists when we have, right, the biggest exponent to our independent variable is 2. And the graph of a quadratic function is a parabola. Right, so again, here we plug in our values in for x, do the math, right, and here's our outputs. Now again, you see, unlike the linear function, we do not have this constant difference or common difference as we go from one output to the next. Right, as we go from 5 to 2, we have a difference of 3. From 2 to 1, difference of 1. We go from 1 to 2, add 1. From 2 to 3, it's add 3. But however, with a quadratic function, while we do not have a constant or common first difference, there is a common second difference. Okay, so this is how we know we have a quadratic function, is when our second difference matches that of a linear function. The graph of a quadratic, as I said before, is a parabola. Right? So we graph these points. We have that parabola shape forming. Alright, so today we're going to talk about the exponential function. Okay, so here's an example of an exponential function, where in these exponential functions, our variable, our independent variable, is the exponent. Okay, so again, very different from what we saw with the quadratic. Right, here we have y equals x squared for our function. Here it's y equals 2 to the x. Right, so again, you can be able to recognize an exponential function when your exponent is the independent variable. And so the graph of the exponential is going to be a curve. Right? So here we made a table again. Here's our x values. We plug those in. Now, when we plug in a negative exponent in for x, right? So if you think about it, negative exponent. Right? Hopefully you learn about exponent rules. Right? Negative exponent doesn't make the output value negative. What a negative exponent does is it takes the base and flips it into the reciprocal. Okay? that's the effect of a negative exponent. And that exponent thus changes to a positive exponent. Okay, so 2 to the negative 2 power is 1/2 squared, which is 1/2 times 1/2, or 1/4. So that's how we got 1/4. Right? 2 to the negative 1 exponent does not equal negative 2. Right? A negative exponent takes the base of the exponent and flips it into the reciprocal, and then that exponent becomes positive. So 1/2 to the 1 power is 1/2. Reminder again, when you have a 0 exponent, so if we plug 0 in for x, 2 to the 0, anything to the 0 exponent is 1. Okay, so now the rest of these you should be able to figure out. So now the graph of the exponential function, as we said, is a curve. So that's what we're going to do with today's notes. Okay, so we're going to sketch the graph of each of these functions. Alright, so we have y equals 3 to the x. Okay, so again, what you can do is you can make a table of values. And some negative numbers, 0, some positive numbers, plug in for x. 3 to the negative 2 power, as we said before, where the negative exponent flips into the reciprocal. So that would be 1/3. And then we're going to change that exponent to a positive exponent. So that becomes 1/3 squared, which is 1/9. Negative 1, plug it in. So that negative exponent changes that 3 into the reciprocal. The exponent becomes positive. So it's 1/3 to the first power, which is 1/3. 0. Anything to the 0 exponent is 1. 3 to the first power, 3. 3 to the second power, 3 squared. These are exponents. Alright, so it's not going to be 6. Okay, 3 squared, which is 9. Okay, so let's go ahead and graph these points. I'm going to start off with the easier ones, the non-fractional values. So I got a point at 0, 1, which again is our y-intercept. 1 at 1, 3. Next one at 2, 9. Right. We get the fractional one, so we got negative 1, 1/3, so it's really close here to the x-axis. And then negative 2, 1/9. So now as we go to the right here, so like if we were to plug in 3 in for x, 3 cubed would be 27. So this is going to shoot up pretty quickly once we get past 2, 9, right? At 3, that's going to shoot way up to 27. Okay, so the thing about here with exponential functions is, the domain, if you're thinking about the domain of the function, right, that spans from negative infinity to infinity. Right, with respect to the x-axis, this curve is going to exist over the entire x-axis. Okay. Now when it comes to the range, now remember the range is the y values, the output values. As you get to the left of this y-intercept, what's going to happen is this curve is going to keep getting, right, shallower and shallower. These numbers are going to get smaller and smaller. Right? You had negative 3 here, this would be 1/27. Right? These output values are getting very small to the point where they're getting very close to 0. Right? But this will never cross the x-axis. The output values will never be negative. So the thing about the range, right? Again, the range of the y values, is that it is going to go really close to 0. Now again, we use the parentheses here to say, okay, we're never going to hit 0. It's never going to equal 0. We're going to get really, really close to 0, right, for our output values. But in terms of how big it can get, well, that can go up to positive infinity. And that can be really big. Alright, I want you to go ahead and try number 2. Okay, so you can see here with number 2 that it looks very similar to number 1. Alright, again, here off to the left, you have this part of the curve getting really, really close to the x-axis. Again, in terms of the domain, in terms of the range, it is approaching, or getting closer and closer to 0. Right, but what you can see the big difference here is that for this curve, right, it doesn't get really steep until much later. Right, what you're going to find is that when this base to your variable exponent gets bigger and bigger, right, this curve is going to get steeper faster, much sooner than it would. Okay. Alright, so now let's go ahead and look at a graph like number 3 and 4, where both bases to the exponent are fractions. So again, take the approach, make a table, and see what happens with your graph. Okay, so go ahead and pause the video now and make your table and graph both these functions. Okay, so when you make a table, right, you plug in -2 in for x. Now again, the negative exponent takes the base and flips it into the reciprocal. So when you flip 1/4 into the reciprocal, it becomes 4. Right? So essentially what's going to be happening, right, so you're going to have 1/4 to the -2 exponent. The negative exponent flips that into the reciprocal. The reciprocal of 1/4 is 4. Exponent changes to positive. So now I got 4 squared, which is 16. Right? So that's how I got 16 in my table. Right? Put -1 in for x. You take that base, you can flip into the reciprocal. The reciprocal of 1/4 is 4. 4 to the first power is 4. 0. Anything to the 0 exponent is 1. 1/4 of 1 exponent is 1/4. 1/4 to the squared is 1/16. So what I want you to notice here with the graph, what happens when we graph these points, is that now our graph is going to look flipped. Right? So now where we have, right, in the previous 2 graphs where we had it off to the left, it was getting smaller and smaller y values, and off to the right it was getting bigger. For these, both of these, which have the fractional bases, right, off to the right it's getting bigger, and then the values are getting smaller off to the left it's getting bigger, and all the values to the right are getting smaller. Okay, so again, this is what the graph for these exponential functions that have bases that are fractions. Right, so to finish up here, I want you to see if you can sketch the graphs for these 4 functions, and then we'll kind of come back to end it and see how you did. So what's different between these now that we have our exponential function, this part of it being multiplied by a factor. Okay, so we're going to see how that affects our graphs. Alright, so the things I want you to notice with these graphs, okay, so let's start off with when the factor that we are multiplying each of these exponentials is a number bigger than 1. Alright, what's going to happen is that our output value is going to go bigger faster. Okay, so what's going to happen is that all these output values are going to get bigger quicker. So what's going to happen is what's called a vertical stretch. Okay, so we have here again, because our base or exponent is a number bigger than 1, we have our curve going this way, and it's going up faster as opposed to here. Again, with our fractional base, it's going to be on the left. Now we look at where we have our factors, which are fractions, values less than 1. Right, we're going to have what's called a vertical compression. So everything's going to kind of look shrunken a little bit vertically. Okay, so that's what the effect of these factors are. Right, it's going to take your values and either make them much bigger faster or smaller. Okay. Alright, so again, if you have any questions, make sure you ask. So again, with these graphing of the exponentials, you want to make a table and make sure you're graphing curves.